Yeah, thanks for coming, and let me start by commenting on some questions that were raised yesterday and that I couldn't answer. So one was this question by Shiraz and then by Suvrat about this Gribov theorem, and it seems that nothing depends on S. Actually, things depend on S, because if you have something like say t to the alpha of s, then the idea is that indeed if you imagine that alpha of s is real, everything goes through, there is a violation. So, but the idea is that alpha of s, it has an imaginary part, there is a branch point, and so therefore when we start taking S.
Imaginary. Just
sorry, it's complex. Yeah.
No, even a fraction. Not an integer.
Not an integer. Yeah. It can be whatever. So, and well, yesterday I had this ansatz where alpha of s was 1. So now on the left-hand side, remember what we did. We consider double spectral density. So we take S to be larger, and so in principle, this guy, if it has a branch cut, develops imaginary part. And therefore, in the right-hand side, I was writing it like this. And yesterday, before all the integrals, everything was real and simple. But here now you have an oscillating phase. Depends on eta prime, because this is complex. And this leads to damping of the integral. The right-hand side was larger yesterday. So now the idea is that it will damp it. But it's an interesting question. So there are some claims. What is the most general solution to this problem? It seems to people make some claims, but yeah, I don't know how solid are they, but the basic picture is the basic answer, I think, is this. Then just to recap, Raghu asked me today, and let me just state yesterday what we discussed. So we considered, so in general theory, the partial waves, they have this, well, with some definition, slightly different. I absorb this factor into the definition of S from yesterday. You can write this formula. So this is an elastic part, and this is an elasticity. And so we discussed how the constraints put bounds on this delta J. And note that unitarity is the fact that the S matrix absolute value in this J basis is less than 1. It tells you that you get this formula, which follows from this. Yes, this guy is positive. And from this also you can see that it's less equal than 1. So, what I was then doing is that I was studying, let's divide this by absolute value. So this is equal 1 plus something. And note that even if each of these things is, if all of these guys are very small, the ratio could be very large, in principle. Let's say f is purely imaginary and small, then this ratio will be very large. So the fact that this ratio is very large, it does not mean that, in a sense, inelasticity is large. But it means that inelasticity is much bigger than, so this contribution is much bigger than this one. And so what we found that this is was much larger than 1 for J larger than 1 and S larger than 20m squared. So there was this ratio of Legendre's, and there was this universal prefactor in the computation that we did. Yeah, so the ratio is large, but I didn't make any claims about size of delta. Okay, that was what we discussed yesterday. So, and again, it was all about gap theories. You often ask, what about gapless theories? It's very interesting. Naively, many of these things fail, but maybe something is possible. And today I will be talking about gapless theories. Today we'll be talking about gravitational theories. So it's based on work. Yeah. Yeah. Yeah.
Conformally, the bootstrap is very powerful because the only data that there is a 3-point function.
Yes. But
in principle, for S matrices, you could have additional data at higher points. So let's say you fix the 4-point function.
yes.
You could have additional data at high. Is there some assumption? A lot of these techniques of elastic unitarity and so on, assuming you do scattering. Is there some statement about why this will fix the S matrix or give you powerful constraints for the S matrix? So I mean, this is what we can do and think about higher points here.
So the inelastic part has in principle a lot of information about the higher point.
Yeah.
Right. This.
You just said that part has to have some value.
Yes.
Constraints came from saying you can't have total elasticity.
Yeah.
So I'm trying to understand if there is
you can bound, I mean, the last result you showed yesterday was telling you effectively delta J over mod F squared.
Yes. Yeah.
In CFTs, you might have thought by examining 4-point functions, you define the CFT.
Yeah.
Here, by examining two-to-two scattering, it's not clear you will define the S matrix, right? Because the inelastic part you will have to keep fixing. That might just have a lot of fun determination.
That's true. Well, even in CFTs, this is a little bit of a formal statement because you have to consider infinite number of 4-point functions with infinitely many external operators. So when you say that it's fixed theory, it's in principle, yes, I agree. So here, in principle, we also can consider all the 4-point functions with all external states, and I mean particles.
You might just have, let's say you had a theory.
So, sorry, here I assume that there is one stable particle, so that's a little bit different, right? Sorry, yes.
Let's say the 4-point function was 0. And the leading, it's like a some Fermi theory, so the leading interaction is, or not Fermi theory, the leading interaction is 5 points for some reason.
Yeah.
Then there's no contradiction in anything at all.
If so, ms equal to 1 is solution to everything. Absolutely.
Right,
So
but the theory has non-trivial scattering.
yes. Yeah. It's but then I mean, if s equals 0, it's not only just 2 to 2 is 0. You are saying that just 2 particles to anything.
No. So I want the leading interaction to be at 5-point interaction.
That's fine, but if you have a 5-point interaction, you have this kind of amplitude.
Yes.
But by optical theorem, it means that you should have this, right? Because the imaginary part of the 4-point amplitude is equal to the product of us. So you cannot do that, yeah.
The elastic part has, I think, a lot of information if you can
understand it.
Different thresholds in principle.
Exactly, yeah. So that's, I think, so note that in Bootstrap, so we write crossing equation and they say the 3-point couplings are positive, and it's a discrete data, but that's it. That's what you're solving. Here we have, in a sense, a little bit more because we have this elastic unitarity, which is an extra. So I wrote crossing equation, which looks very similar to, to Bootstrap. Apart from this discreteness, we can write fj of s, pj is equal sum over j, fj of t, pj. But now these f's, not only, they also satisfy on top of this non-trivial constraints. Yeah, it seems that it has a lot of data. How much data it's how powerful it is, it's hard to say. But I feel also in Bootstrap in Bootstrap formally it has everything if you include all the external states, but in practice we have only finite number, And I think it's more or less an open question, actually, what's happening. Yeah. So today I would like to talk about the works that should appear soon with Murat Kologlu, Peter Kravchuk, and David Simmons-Duffin, whose name is usually written like that. And I will be talking about gravitational theories today, so forget about the gap. And for many of the arguments, I would like we think about theory as being classical, as classical gravitational theory, but at the end we would like to say that everything we say holds for any quantum theory of gravity. So the idea would be that this is a principle, this is the rules of the games, but we cannot prove this in flat space, but we can prove it in ADS. And so the picture in ADS is very simple. You have this classical picture, and then you have a natural generalization to quantum picture because you have this OPE. Here we do not have, as we discussed, if we have a quantum gravitational S matrix, we don't know what are its properties, what is the set of dispersion relations one can write. But so here we would conjecture in the end that what is the dispersion relation one can write in a theory, and this will be motivated by the discussions of causality and by ADS. The idea that we would like to understand is the following. So in general relativity, we know that if we drop a stone and a feather, they're supposed to fall the same. They will take the same time to fall, but because things in GR follow geodesics, does not depend on the internal structure of a body. This is a very special property of GR. And if we modify gravity, so we know that if we add high derivative corrections, this is not true anymore. So particles do not follow geodesics. Things, for example, propagation of light will depend on polarization of the photon. But the idea is that there is some principle which substitutes this principle that all things follow geodesics. That roughly that's generalized to any theory of gravity. So we sort of call it string equivalence principle. And so the idea would be to derive what it is and to explain why we think it might be true.
Is this classical or?
And then it's all will be quantum. So the idea is that any consistent S matrix of gravitational theory satisfies this principle. We cannot prove it in flat space or de Sitter, but we can prove it in ADS. So this is a conjecture. But for many of the arguments, so I will be now talking something about classical things, but then I'll switch to amplitudes, and I will be writing expressions solely in terms of amplitudes, and then you just, whatever amplitude you have, you should plug and...
I'm just confused by the terminology equivalence principle, which of course is, as you said, the classical.
Yeah. So made the quantum some version.
You are going to define.
Yeah. I was going to define what I mean. Yeah. But yeah. So one nice setup to study this sort of questions is to motivate it to study the propagation through the shockwave geometry. So consider shockwave. It's given by this metric. So this is the transverse coordinates, and the shockwave is localized at u = 0. So here. This is a metric of energetic particles moving with the speed of light along v direction. It's an exact solution of Einstein equations. So this component, HUU, it satisfies Laplace equation in transverse space, the y transverse.
It's a shockwave in flat space?
Yeah. It's proportional. It's equal to delta function in this transverse space, and then this is a source. This is a stress tensor in Einstein equations. So Einstein equations just because, well, whatever, g mu nu equal t mu nu, and this reduces for this space-time to this equation. So the stress tensor is a particle localized on this line, and so in principle we have a transverse coordinates. So here the source is here. Now, one nice property of this geometry is also that it's an exact solution in any theory of gravity, in the sense that if you add high derivative corrections, this geometry has some so there is delta of u here. So it's localized here, and it's localized here. Yeah. Now, if you consider a propagation of a probe through this geometry, there are two effects. One is that you get a kick in a v direction, which is defined by if you send a wave packet at some impact parameter b, you get a kick in the v direction of this type. There is G Newton here, and so the fact that it's G Newton m is attractive says that this is positive, and this is a statement of Shapiro time delay and related to causality of the theory. And the second effect is a kick in the velocity, because this is an attraction center. So when you cross the shock, you get a kick in the direction of this gravitational center. This is a geodesic on this background, and another interesting property of this geometry is that, in principle, you can consider superpositions of these guys. So you can consider, many shock waves, and send your particle through. And so this is the first shock. You can put second, third, etc. And the effect for geodesics is just additive. So what happens is that your particle accumulate delay, get some kicks, and in particular, the effect, let me send the separation of shocks to 0, so I can put them very close to each other, on top of each other. The order at which you put this shock does not matter. So shocks commute in GR. And this is one expression. Well, this is a special property of GR, which is violated in high derivative theories of gravity.
What is the special property?
That propagation through shocks commute. So there is an ordering of shocks. You could have ordered it differently, and in the generic theory of gravity, the order matters. In GR, the propagation is commutative.
Is this true of the linearized approximation?
Well, this is an exact geometry, and this is a geodesic. So this is a statement about geodesics at the moment. Yeah.
Sometimes you're not taking into account you just like that because the shocks are just passing through.
Yeah. You should, in principle. Yeah. You they are non-interacting here, but that's. I guess you worry about that, but at least in say perturbatively, in any theory of this is an exact solution, you can superimpose the shocks as you like. But no.
Special to parallel shocks.
Yeah, they are all parallel here. Otherwise, they will start interacting. Okay, that's just exercise in yeah.
Is it given that exacerbation also true for theories of the kind 5 times r? And you have a scalar term?
I think if you, I think yes, because you can set phi to 0.
What's the question?
Is the statement that there's an exacerbation also true for theories where you have 5 times r and a kinetic times in terms of phi?
Yeah, but this, he didn't say what the stress tensor was made of, so I mean,
Yeah.
phi doesn't appear in this equation.
But the shock is going to source something for the scalar field, right?
The shock.
The stress tensor given through gravity.
That's what I'm
Okay, I thought that so at least in some minimally coupled theories, you can the solution is you set matter to 0, and then you it's consistent.
He's talking about some diagram in which two particles that make up the shock collide and release a graviton, and then they, but that can't happen. Right?
So let me proceed. I will anyway restate everything in terms of S metric. Then it will be to talk about it. Right. The interesting thing is that this is a geodesic computation.
Hi, I have a question. Hello.
Hi.
Yeah. So the statement that you can add multiple shocks, is it a perturbative statement or an exact statement in GR?
Exact.
Okay. Thank you.
Yeah, it's important that they're parallel to do that. You can here add any functions f of u and any harmonic function in a transfer space. This is, I guess, more generic, whatever PP wave or how's it called solution. The interesting thing about this computation is that if you think about, let's say we send a photon or a graviton, the propagation of a photon or a graviton is described by some wave equations, and then, well, you know that these things should follow geodesics, so this will also be true, but it's not obvious, at least naively, by staring at the wave equations, that it comes about this way, and of course it does. So let me try to restate this computation as a computation using scattering amplitudes. So what is, we would like to understand what is this, how to think about these processes sort of on shell, and what is the meaning of this commutativity of shocks?
Commutativity of shocks, you're referring to not the fact, you said it breaks down in higher derivative because they don't follow geodesics.
Yeah, exactly, yes, that's the idea, yeah. To simplify the discussion, even though I believe that you can generalize to most general case, let's just consider two shocks. This is a simple situation where we can analyze this problem. So we would like to consider some process of this type. We have shock 1 and shock 2. And we have some probe, 3, 4. So this would be, this looks like a 4-point amplitude, but this 4-point amplitude will be a little bit special because imagine you would like to create a state which is a shockwave state. Let me introduce a notion. So now we're in Minkowski space. We consider scattering amplitudes in Minkowski space, and we would like to consider scattering of the shockwave states. So what is a shockwave state? So we would like to have something like something localized in U, as you see there, and we would like it to be harmonic, say, in the transverse plane. And for discussion of scattering amplitudes, we can take the wave function to be a plane wave but the fact that it's on shell here says that q square is equal to 0. So this is not what you can do in a Euclidean space, right? Because this is Euclidean momentum. So q is a complex momentum in a transverse space. And the way one can think about it is that these shockwave states, they're not really physical states, but this is an effective description if you would attach here a particle. And here a particle, and this was this shock waves. So this source here was a particle, and this kick was due to the shockwave geometry. And so the picture was that this is a particle, it sources the shocks. And so in principle, what we are doing should be possible to formulate in terms of normal, but higher point amplitudes. But higher point amplitudes are complicated, so instead, the idea is that we can just cut off these things and consider the scattering of things made of this complex momenta. And this, of course, we can rewrite as an integral over energies. And here we have just some PV u0 over 2 times e to the I p y, where we choose the momentum to be 0, PV, and Q. So the metric is you see the metric is d squared equal to minus du dv plus dy squared. So this this state is null. So this is on shell, p squared is equal to 0 because we imposed this condition. And also here generically for this shockwave state, we will consider polarization tensor to be purely along, say h mu will be purely along d will be purely along du squared. So it will be some kind of, usually again not the usual polarization tensor that we choose for graviton, but it of course satisfies the fact that HUU contracted that P mu H mu nu is 0, because H is just HUU and PU, which is this component at 0. So this is a shockwave state. I'm not writing it here. So this is a shockwave state.
Just to understand, you have a graviton with a certain polarization, and the 3 and 4 correspond to scalar particles. So what is it?
Yeah, so 3 and 4 is a probe. It is this particle, and it can be whatever you like. It can be a normal physical graviton, normal physical photon, and scalar particles, and 1 and 2 are shocks. So now, okay, we can consider this 4-point amplitude, which is analog of this, and we can ask what is this ordering? Now we can order shocks as 1, 2 or 2, 1. And the idea is that, well, we take this wave function, so we have integrals over dp1v, dp2v. We have
Sasha? Sorry, I didn't quite understand the setting for the later, the way you formulated it later. The shock seems to be on one side of this probe and not on the other side. So what exactly these dotted lines mean?
what exactly what means, these lines?
The dotted lines, 1 and 2.
Dotted line means an external state with this following properties. It has this momentum with the complex momentum and transverse plane and the polarization along the U component. So this is equivalent to a 4-point amplitude with, polarization tensors and some momenta, where for states 1 and 2, you chose polarization and momentum as I explained. So dotted line means an external state was defined as I explained here.
I guess the question is usually if you have one state, it would go through the 3-4 line, right? And just one shock would correspond to a 4-point. So here it seems it should be a 6-point function.
So yes, that's what I was trying to explain. So usually this shockwave process is described like this. You have a source, you exchange the shock, and you have a probe, right? So this is the interaction. So let's try to explain. So now if we have two shock waves, we have scattering of one source, and then this guy proceeds, and then it scatters of another shock. Let me say it's called, I don't know, 1, 2, and 1 tilde, 2 tilde. So scattering of two shock waves is described by 6-point amplitude. That's what we want to do. But now the idea is that we're considering the high energy limit of the 6-point amplitude, where we want to cut off these guys. And effectively, cutting them off means to considering a 4-point amplitude, where now the states are not physical states, but shockwave states, as they defined. And you can check that if you glue these guys back, when you're considering a shockwave geometry, you're effectively doing just this.
But what happens to the shockwave geometry for V less than 0?
For V.
I mean, on the other side of this probe.
I'm not sure. So the shockwave geometry is localized for any V, and it has non-zero support for any V, and it's localized for U. And the same true for this wave function. It is non-zero for any V, and it's localized in U. So
I'm just confused because your dotted lines don't extend past.
No, that's the dotted line. These are really these states. So they're not localized in V. They're not. This is what dotted line is, and as you see, it's localized in U. It's harmonic, and it's everywhere in V. The same as was before.
I think
Okay. But then it has a feeling of 6-point function.
I think maybe that's the confusion. The dotted line going past when
Maybe I can draw like this.
the geometry.
Yeah.
This is
Yeah, I think it is like a 6-point function. But I think he will eventually look at it as just scattering and scattering. 2 4-point scattering.
that's what
Whole thing is 4-point.
that's what we are doing. But the idea is now to just consider 4-point amplitudes with such states. And in the regimes of when your theory is classical and you know what you're doing, you will just reproduce shockwave computations. But in a quantum theory, you get what you get. So let me write, maybe it will be helpful. So we have this momentum. Q1 squared is equal to 0. This is for the first shock. The second shock we get 0 V Q2 square. And then for the probe, we have, say, we choose PU 0 minus Q2, and P4 is equal minus PU 0 minus Q1. So that's the kinematics of the 4-point amplitudes that we want to consider. This the polarization guys of these guys are funny.
Can you repeat what you said about the high energy limit and reducing?
Well, so here I haven't precisely said. So in principle, let's take a 6-point function in a physical kinematics. We know that if we take a limit when the relative energy between these guys and relative energy between these guys in the gravitational theory, it reduces to the shockwave computation. And but now we want to consider a simpler object which reproduces this result, and we define this object like this. So this is as a 4-point amplitude with in a sort of mixed signature. This is a mixed signature 4-point amplitude. And
you will say how, what kind of a complex solution you're taking to Q vector square equal to 0.
Sorry, say again?
Can you say more about what is the complex solution that you're taking? For example, in the BCFW deformation, we take a particular kind of complex solution. Right?
Yeah.
You add some Z and say,
yeah.
So is that something like that you're doing? I mean,
well, if you wish, in the end it will be, so we have this amplitude of function S and T defined in some domain and for some polarization tensors, and we using it for, in a sense, for the same S and T, but for polarization tensors which are maybe slightly funny. So I think we are just studying a 4-point amplitude at the moment in a particular setting. So
just polarization tensors, right? You're deforming the momentum.
yes, but the amplitude depends on just S and T, right?
But not if you have I mean,
Not if you defend, not if you have some prefactor, if you have some dependence on polarization tensor, which is polynomial, right?
that's true, but if you change the momentum, you could just not tell the amplitude changes in as S and T. I mean,
So
the momentum, you're complexifying the momentum, right? That's so you're right.
well, so let's say let's write a 4-point amplitude of gravitons which has some polynomial prefactors, involves polarization tensors, say, and then a function of S and T, right? Which is.
But sorry, those polarization tensors may dot with linear functions of T of the momentum.
Exactly, yeah.
So you might have epsilon dot K.
Exactly, yeah. Yeah. Right.
And now what do we do?
Now we evaluate these polynomials and these kinematics, and then we will be studying, the rest will be just, in a sense, in the end, I will be just talking about the properties of these functions of S and T.
And you're saying that all inner products are left invariant by this field?
Yeah.
All the STU are real?
Yeah. S and U are real. Yeah. I think so. We can choose them to be real. So S and T will be real, and in the what we are maybe it's not the best way to motivate it, but I thought that's how we came about thinking about this. And in the end, we will be just making claims, statements about this function of S and T for S and T being real. Yeah.
You had just had one shockwave.
Yeah.
And you're taking this high energy limit. Then you're computing the expectation value of something in this state.
Yeah.
Maybe just looking at that to tell me what Q bar to choose.
If you okay, so you just I think essentially what you will, if you will do the shockwave computation, that's related to the fact that shockwave computation I formulated in impact parameter space, and at least with shockwaves you have this propagator, and when you go to impact parameter space you can close the contour, and effectively things in the impact parameter space are just controlled by null Q, null complex Q. So if you integrate, so you have these harmonic functions, you can rewrite them in momentum space, and then you're taking the Fourier transforms of amplitudes for real Q, and the Fourier transform of this amplitude has the properties that when you evaluate them, they're given by residue of the pole, and the pole is exactly this. It's Q square 0. This is the fact about impact parameter space, that somehow amplitude in mixed signature are related to impact parameter amplitudes in usual Minkowski. So the way you reproduce it is this way. In particular, this shock wave 1 over y is equal to 1 over q to some power. And and this 1 over q to some power is an amplitude. It's just a propagator. So, and then when you do this Fourier transform, it's given by a residue when q squared is equal to 0. So that's it. And we, in a sense, this amplitude is a residue that you get when you close this contour in the 6-point amplitudes when you go into Fourier transform. Maybe that's a better way to define it as a residue, as some certain residue in the 6-point amplitudes.
Like if actually gonna put one.
Excuse me, Sasha.
Yeah.
Yeah, sorry to press on you a little bit. So should I think of this as a single particle being exchanged between the shockwave geometry and the probe, this dotted line, as a graviton or something that is getting exchanged?
Yeah, here it's a graviton. It's a graviton with this momentum and this polarization here.
These dotted lines, right?
Sorry?
The dotted lines are to be thought of as graviton being exchanged by the shock wave, right?
This is a graviton, yes, this is a graviton being exchanged here.
I see. So the full effect of the shock wave geometry would be obtained by exponentiating this effect somehow?
Yes, I think so, yeah.
So even at the linear level, you would impose this commutativity?
Sorry?
Even at this one particle level, you would impose a commutativity?
It's the same. So if when you exponentiate, you just exponentiate a commutative effect.
Okay, thank you.
Okay, so let's study this object, and maybe I don't know if it's useful, but so an analogy is that for example, in conformal theories, or in QFTs, we have let's say in CFTs, we have local operators, which are analogs of physical particles in ADS, and we have light ray operators, which annihilate the vacuum. Light ray operators are also physical, even though they annihilate the vacuum, but you can study correlation functions of light ray operators in some states. So the shockwave state is a flat space analog of a light ray operator. It's not really a physical thing, but you can study it. And you can, like light ray operators in CFTs are sourced by by two operators convoluted with some kernel. Here the idea is that the shockwave state is also defined in this way. So yes, in CFTs, this story is a story about correlation functions of light ray operators.
The complex momenta are the analog of the complex angular momenta.
Maybe it's some kind of continuation momentum as continuation in angular momentum. I can say yes, yeah. But also it's not necessarily. If you take an A-neck operator, it's just integral of a stress tensor, right? It annihilates the vacuum. So this gravitational shock wave is a flat space analog of an A-neck operator. In particular, in CFT, this computation is a 2-point function of A-neck operators in some state created by a primary. That's the idea.
Sorry, just a question. So Q1.Q2 is real?
I think so. Well, let's choose. We can choose it. Yeah. But even if it's not real, as we discussed this, so let me write Mandelstam invariance. S is equal to minus 2 Q1.Q2, and T, well, the way we defined it, it's a bit confusing, maybe, but is this. So even if it's complex or real, as we discussed, the amplitudes are analytic in this variable, so we can choose them to be real, at least in high enough number of dimensions. But I guess we would like to be in high enough number of dimensions to avoid the discussions of infrared singularities. He would tell me amplitudes do not exist, and so, yeah. Okay, so this being said, let's proceed. We would like to now do something like this. And we convolute this with a usual amplitude in the momentum space. So I will do scalars for simplicity. So let me define this. So these factors come from the positioning of the shock, and this is the integral that we have here. So there is some trivial delta functions.
Small d same as the capital D.
I'm sorry, yeah, I switched. So some more QIs, some a delta function in the u direction. Part is, let me call it a q function, q as a function of u1 minus u2. And this function is defined as I over pu, the integral dt e to the minus I over 2 t over pu delta u times t s and t. So this is the object we would like to study. That's just an amplitude, which we integrate over one of the Mandelstam variables from minus infinity to infinity. And the delta u appears here. So you see what we did. We used momentum conservation in the v direction. So P1 and P2. Sorry.
Just to be clear, so on the field, on the conformal field theory side, it's like 6-point function of 6 primaries, and you are doing 2 OP, and each OP is giving the light ray operator. So 2 light ray operators and 2 primaries. Is this correct?
Yeah.
Okay, thank you.
This is the object, and the integral over t goes from minus infinity to infinity. We have 2 cuts. So the contour you should take as the usual one. So this is a t-plane. And now you see that, well, I guess this is an assumption, but again, if you think about, if we're less ambitious and say about classical theories, then it's obvious. In a full quantum theory, it's an assumption. Namely, if you note that depending on the sign of delta u, the amplitude will decay in the upper half plane or in the lower half plane exponentially. And so if you assume that the amplitude is sub-exponential in this complex domain, you can close the contour. So we can either...
I didn't understand the picture. So why is there a gap between it? It's gapless theory, so...
No, it doesn't matter. So this is 0, this is minus s. Yeah. If you can close the contour, if the amplitude decays exponentially, sub-exponentially, you can close the contour and rewrite it like this, or we write it like this, depending on the sign of u, right?
So this is sub-exponential for fixed S large T behavior, right?
Right, yeah.
So in quantum field theory, that is presumably true? That it's
Yeah, in QFT, this is definitely true.
Yeah. Okay, so it's an assumption because we're talking about quantum gravity.
Yes, it's an assumption in the quantum gravity. Yes.
Thanks.
This is delta U. So in particular, we can close the contour, say for delta U larger than 0. So we can write that q of delta u is given by proportional to the integral from 0 to infinity dt disk t a s of t. So we close the contour to the right, and for delta u less than 0, we close the contour to the left. And this is proportional from minus infinity to 0 dt. The same thing.
This is string theory, for example.
Tree level?
Tree level.
Yeah, then it's surely you can do that. Yeah. It's just polynomially bounded in string theory.
I mean, but if you start continuing with the complex plane, you could get.
It's t to the s, right?
It's t to the s. That's right. So.
Sub-exponential.
It's sub-exponential, yeah. No, in string theory, it's yeah, it's t to the.
Yes, but I'm wondering when you do this analytic integration, you at any time go to some cross, which will determine s as t or t. That's going. It doesn't. There's no regime where you should think of the amplitude as s to the t rather than t to the s.
No. Well, we have s being fixed and we're integrating over t, so.
Yeah. But are there no other singularities?
Yes, that's again an assumption. That's an assumption that we have this minimal structure. So thank you for bringing this up. I'm assuming this minimal structure. So. Now, now let me, and again, maybe in CFTs it's the kinematics is more complicated, but in CFTs it's all true. So in sort of all the steps you do there are not assumptions, but they are rigorous. But here it's true. If you believe there are some exotic singularities somewhere, then we will have to pick the contribution from the singularity. So there will be an extra terms here. Closing the contour.
The second integral, I can take the upper limit to be just minus s.
Sorry, say again?
The last line. Upper limit, can I just take it to be minus s?
Yeah. It will be minus s. I just wrote it. In this way, discontinuity will be 0. Now, here there are also exponential factors that I didn't write. And I didn't write them because remember in the computation with shockwave to discuss commutativity, we can take a shockwaves on top of each other. So we send delta u to 0, and then the statement of the commutativity of shocks is the statement as you take delta u to 0 in this expression or in this, if these are equal or not. So this is
limit in the second integral is minus infinity to minus s.
Yeah, but I'm using the statement that disk of t can be 0. So you can integrate to 0, but discontinuity is 0 there. Now, if we take delta u set to 0, first of all, you can ask, is it allowed to take delta u to 0? And because you see here it was an exponentially dumping, some exponential dumping, and you can ask, does this integral exist, etc. And again, for now, let me assume that it exists. It will. This is a part which I told you that we do not, again, in flat space, we conjecture that the amplitude do not grow too fast with energy. And this is the same growth which you get in the consideration of asymptotic causality. And in QFT, it's all rigorous. But in a gravitational theory, let me assume that this limit exists.
Why do you want to, delta u going to 0, why you want to take that limit to?
I want to put these guys on top of each other and discuss the commutator of shocks. define the commutator of shocks.
So if you just had a bunch of discrete poles, for example?
Yeah, then it will be sum over masses, blah, blah, blah. It will be, this guy will be sum over residues. You have three,
We'll have delta function.
As a delta function?
yeah, it will be 3, 1x,
All the string
x.
facet states.
Exactly. We will discuss string theory. So this is this, and this one is equal to 3 to x, x to 4. So this is.
So I was only worried, I mean, in the sense that string theory tree level, all the poles are on the real axis.
Yeah, yeah.
But, in the loop, with loops, they will go.
They'll go on the second sheet.
Oh, they go on the second sheet.
Yeah. So you will have a cut.
Oh, so only the stable particles.
Yeah. Right.
So you're closing the context.
Yeah. Yeah. So this exactly in a tree level theory, you get a bunch of 3-point amplitude, and again in maybe a useful analogy in the CFT, it will be nothing but the OPE, and the operators will be single traces. So in a large N theory. Okay, but now let's write the commutator. So we would like to write Q0 plus minus Q0 minus. And what you get in this scalar case trace all the signs. So in particular, if you want it to be equal to 0, you get that the integral of a discontinuity is equal to 0. So this type of relation, the discontinuity of the integral of a discontinuity equal to 0 is has a name. It's called the superconvergence relations. It was studied in QCD in the 60s, so it's due to De Alfaro, Fubini, Furlan, and Rossetti. And the way you derive it is, of course, very simple. You just take an integral of an amplitude around some random point. And then if you assume that your amplitude decays fast enough at infinity, you deform the contour. So you have the contribution from the cuts. And if you can drop the arcs, you end up with this relation. So this is equal to 0. If you pick a random point, the amplitude is regular there. So this integral gives you 0. And then, of course, the crucial part is to drop the arcs. And dropping the arcs related to the radio behavior. For example, here, to drop the arcs, the amplitude should decay faster than 1 over t. And this does not look very physical in a scalar case, but in a gravitational case, it will become somehow spin makes these things better. And in particular, GR, tree-level GR, will satisfy these superconvergence relations. So in this, this shockwave states are such that if you, say, take a 4-point amplitude and you...
Isn't in tree-level GR, A grows like T squared or something?
A grow like T square, but somehow, so there is a, so I told you this, the way you do it for particles without spin, but if you include spin, that the way it comes about is that it does not grow like S square. It actually, well, if you take all the factors, it satisfies this condition, and the way it comes about, it's a little bit. The structure of polarization tensors is such that this large growing term is 0, is set to 0. And so you end up with an amplitude which satisfies these relations. I will try to maybe explain it better. But for now, what we just derived is the statement that the superconvergence relations and commutativity of shocks is the same thing. And the fact, if you can ask when do the shocks commute, from here you see that the shocks commute when the Regge limit is soft enough. So if the Regge limit is soft enough, you can write a relation like this, drop the arcs, you get this, and reproduce commutativity of shocks. So that's a punchline of what I said so far. Yes?
So the statement of superconvergence
Yeah.
is the same as validity of this main BCFW recursion. There also you need some
Yes.
contribution at infinity to validate.
Yes. Right. Yeah. That's right. Yeah. It's yeah, I agree. This is very similar to BCFW, and actually, one way to think about what we are doing is, or I guess it's a similar thing in a sense. It is BCFW. Then.
String theory, for example, it's not in detail the same thing. It's similar.
I mean, it's similar. It's similar in BCFW. It's slightly different. You write here t minus t prime. So you write an amplitude, and then you reduce amplitude to the sum of the residues. Here, you don't want an amplitude. You want a zero.
So it's important that for them, all his t's and so on will be real. And you want you complexify things.
No, here also t.
No, but when he did this complexification, it was not a BCFW.
No, that's right. But I think what Loga is now talking of is the behavior at infinity in the t-plane. Whether that is similar to the z behavior in the BCFW.
It's not clear that it's exactly.
Yeah. Because it's
t squared in just pure gravity.
Yeah.
The BCFW limit will still behave well. That depends on some choice of polarizations and so on. So it's not exactly the same thing. But just in pure
I
gravity,
also don't know whether it's the same thing, but I will just say what Loga was saying. Yeah.
This limit of E is large enough T, it has to be smaller than 1 over T.
Here, yes, yeah.
But your T and A, capital A are the same, right? I mean,
Oh, sorry, yes.
you switch with
I'm sorry. Oh, yeah. Okay, now let me switch to this claim that I would like to. Yeah, I will talk about string theory in 10 minutes. We will see. This is satisfied in string theory. I will discuss string theory in.
That's surprising from a physical point of view. The shocks should compute string theory.
It's actually not. It's related to the fact that space-like separated vertex separators on the wall should commute. So you can solve the string theory in the shockwave background exactly, and there it's manifest, sort of. But the way it comes about is not completely trivial. So if you look at the shockwave, so there is a sort of shockwave S matrix in string theory, and this shockwave S matrix, they sort of trivially commute. So so there's two shockwaves that trivially commute. But if you try to interpret it in terms of the residues, this commutativity requires stringy modes. So that's a picture.
You're going to use this as a kind of a criterion
Yeah.
for your
Yes.
equivalence principle.
Exactly. So basically, if you take it for 4-point gravity amplitude, consider this proper kinematics, then the claim is that that's what should be satisfied in every theory. That's a hypothesis conjecture. Huh? I would say, well, the conjecture in every theory in CFT, we can prove it. If you have a consistent CFT, you can prove the analog with it.
You could think of does not happen, right?
Oh, no, but this should not admit UV completion, the idea. So here we assume that UV, we have to assume that the theory is,
So it's satisfied in flat space tree-level string theory.
Yeah.
It's satisfied in any CFT.
Yeah.
You will show.
Yeah.
And you will say these are
Yeah.
so these are theories which have good UV completion.
Exactly.
But it's not satisfied.
Yeah, and so if you add something where these things do not commute, people discuss other problems. For example, this analysis of asymptotic causality in Gauss-Bonnet, you see that it has non-commutative shocks.
How is it related? Will you say something?
Yeah, the statement is that, which I don't think, at least I haven't seen in the literature. So the statement would be that we look at some properties of this in this Shapiro time delay. We look at the property of the graviton residue. So you propagate, as I discussed. It's in the shock waves. It's all controlled by this 1/q square, or 1 of the propagator exchange. And so we study properties of this residue and try to argue that it has to be a certain way. This story is about Reggie, right? So this all follows from the Reggie behavior. So the claim is that, so in our causality story, the amplitude should not grow faster than s square, sort of, because if it grows faster than s square in the signal model, we had, so if you have a causal medium, the S matrix through this medium, it had the analytic in upper half plane in a causal thing, but also it should not grow faster than whatever, it should be bounded by 1 absolute value. And naively, the statement that in the Gauss-Bonnet theory, the amplitudes actually, if you look at this kinematics, they will grow faster than s square. So they will grow faster than s square, and if you would run the same argument, you would see trouble much simpler in the sense that you just see that so we were trying to focus on the part of the amplitude which grows like s square but has a wrong sign. And this part focuses on the part that grows like s cube, say in Gauss-Bonnet. I think this claim was never observed because no one ever computed 4-point amplitude or 4-point correlator in Gauss-Bonnet. So in a sense, this is the nice thing about this is noted that we start with some complicated 4-point amplitude. We make a statement about its Reggie behavior, and then if this is true, superconvergence should hold. But to test superconvergence is much simpler because it's reduced to the statement of 3-point couplings which are known on shell. So for Gauss-Bonnet, you just plug this thing, you plug these things, you subtract, you get non-zero. It immediately implies that the arcs are non-zero, which means that it grows too fast in the Reggie limit. And in CFT, it will violate bound-on chaos. That's the idea.
There's some way to state this more formally in terms of condition on commutators and scribe class. Because that's the asymptotic causality thing you could really state in terms of commutators and operators and scribe class.
Yes.
Is there a way to relate that in a direct way?
I would love to have such a formulation. I couldn't find yet, but I feel that something like this should be possible. But
So QCD does not satisfy this, right?
for scalars, not, but for the spin 2 glue balls, I suspect it will be satisfied, actually.
I was just thinking, if the total amplitude grows with...
Yeah. But so, okay, we haven't discussed carefully the situation with spin. But I think that, okay, I have to think about it, but my expectation that it might work for spinning glue balls, it might work. And also, right, I think people might have discussed it even, but I agree. At the moment, this is not what you have for scalar particles in QCD, for you cannot write such a relation for pions. So, but that let's not...
The alpha, what did they do?
Oh, they study. So the idea was that yeah. Well, so that's I thought how, at least that's how I was told So Veneziano was thinking about his formula that, so there was an experimental data, and so one way you can do that is you can keep this contour up to some finite radius, keep the arcs, and then you don't need to do that. And then the idea is that you approximate these arcs by a Regge theory, and you take an exchange by Rho meson in the dual channel, and the indirect channel you can take the experimental data. So few resonances, and then you try to match the two. And so this was this idea of duality, that to reproduce a Regge behavior in the T channel, you don't need to introduce new things. The same particles in the S channel reproduce the T channel behavior. So there are these plots, where you plot the Rho meson Regge behavior against these integrals, and there is a good matching. So that's I think what they were doing.
Drawing a distinction between scalars and spinning objects, it is in the probe or the shockwave state?
Shockwave states. Yeah. Somehow the shockwave states. So
probe doesn't matter. Probe could have any spin.
Probe could have any spin. Yeah. So what matters is the spin of the shock. Maybe there should be a good understanding. It's the same happens in CFTs. If you consider light ray operators of spinning primaries, all these operations of taking them, putting at the same time, this becomes better behaved. So in principle, again, somehow the spin helps in this story. Right. Maybe let me write the spinning conditions exactly, so that we have something more precise to discuss.
Sasha, this statement that you made needs to be valid for any value of S.
Well, in principle, this thing will depend. It should be valid for only some values of S, I think. And so,
where was the choice of S in your?
In my choice, S is arbitrary, so this is equal to 0. But when you're dropping the arcs,
yeah,
you are making a choice of S such that arcs are small. So that's where the condition and when you can drop the arcs follow. And I think we would like to say that for sort of physical S, you should be able to drop the arcs for S negative. But
for any physical value of S.
I'm not sure, actually. I'm not sure about it. Say in string theory, in tree-level strings, this is not necessary. Yeah, I'm not completely sure for which S it will work. Sorry, yeah.
Okay.
But this is where you have to be careful, and that's where where you make this choice. So I think for the spin, I don't know if I should write it, but well, I think for the spinning case, it's again you just take the integral over, say, dz minus infinity to plus infinity. You take the discontinuity of an amplitude with the polarization tensor chosen for shock waves as follows, and then you take S and Z T, and that's just has to be 0. Okay, I don't have a forced lecture to answer well your question, what happens to S squared, I'm sorry. So let me now make a claim, and then I will quickly proceed. So if we consider tree-level scattering, the claim is that non-minimal coupling gravity to gravity leads to non-commutative shocks. By this, what do I mean? You take some probe, whatever you like, you take one shockwave state, you take whatever, some other shockwave states, this particle can turn into something else. And this is an example of non-minimal coupling. It can be some y could be x. So this is so if you impose something like this, so now I'm doing a simple tree-level analysis. All the 3-point amplitudes are known by kinematics. So if you say that this equal to 0, then the only solutions to these equations are minimally coupled matter and GR. So as soon as you start modifying 3-point couplings by adding something extra, you violate these conditions, and therefore some extra stuff should come in and fix the problem. That's the idea. Now let's discuss string theory, because I'm already over time. Yeah, we can discuss maybe some example, but I don't know. If you simply write any 3-point amplitude, they're all known, and you take any non-minimal one, so the simplest will be probably something like 2 gravitons coupled to a scalar, something like Riemann square times phi. Then you will see that this is non-zero. And if you plug 3-point amplitudes in GR or in electrodynamics, you will get that they are all 0. Now let's consider graviton scattering in tree-level string theory. So in tree-level string theory, we have amplitude given by, say, k left, mu1, mu4, epsilon mu1, epsilon mu4, k right, say mu1, mu4, epsilon mu1, epsilon mu4, and the famous factor so these kinematical prefactors, they are known, and so depending on the strings that you are studying, they're different. So usually, let me define the basis that we need is that there is what you get in a superstring, and then bosonic string, and so you get
This is for 4 gravitons.
4 gravitons. This is 4 gravitons, yeah. So in say superstring, for superstrings you get this square. For bosonic strings you get k bosonic, and for heterotic string you get k bosonic times what you get in this, I guess type 2 or whatever. Now these prefactors are known, and they are something. One thing that you...
Mod square, right?
Sorry?
Just what you really get in the string is a mod square from the left to the right.
Mod?
Well, and it may not be important, but you really get the you get the absolute value square in each version.
Okay.
Satisfied for the complexity.
Well, but everything, so here, so the epsilons are real.
Yes, but the momenta are not real.
The momenta are not real. Yes, okay, let's, we can put this guy here, but
And then what's where I remember because you get 1 by z and 1 by z naught.
yeah.
Now, I'm not sure how the momenta enter that. Maybe you don't get a 1 square complex in mind.
Okay, well, let me, so there is the only thing which is complex are Q's, I think, and so we can choose just all scalar products to be real. All the Mandels, so this is depends on scalar products, let's choose them all to be real. So this factor, and by the way, note that if you look at the 3 graviton coupling, this is the one of GR, so this is manifestly has shock commutativity. We have nothing to say about this. But here you have already Gauss-Bonnet thing, and so if you choose X and Y to be just gravitons, and you just take a graviton pole, this is non-zero, which means that the string states should come and fix the problem. So let me write. Sorry, yeah.
So you're saying that the heterotic is.
It's there is non-minimal coupling, so there is bosonic time superstring, and so this KSS in the kinematics of interest, it's say pu square times s times e3 dot e4, where these are transverse polarizations for the probe, and k bosonic in the kinematics of interest, it's pu square times s. And I think this is maybe partially answer to Raghu's question. So note that this, so this s here, they usually this guy will behave as 1 over s square, let's say large S, and so here you get something like s to the 4. But we will not be taking this s to be large. The kinematics was choosing such that we will be taking large t, so the other variable, and so all these factors. All these prefactors, which usually give you this growth, that they will actually depend on t in a way that is not growing. So here you have something again, which does not depend on the naively of the order of the shocks, because shocks, it's a permutation of 1 and 2. So you get something like again, this, remember, there were four momenta and polarization tensor of a probe. And then there is an interesting term. So this is the answer for this K bosonic, which is non-commutative on the gravitational pole. And the way it comes about is quite neat. So you have here E3 Q2, E4 Q1, and here you permute Q1 and Q2. But the important thing is that this prefactor, say, has a gravitational pole at t equals 0. Now when you compute the residue of this gravitational pole, because of this extra factor of t, this guy will not contribute in one channel. So in t channel, when t is equal to 0, and say this is this first term, when you go through the shock in the order 1, 2, it's the same as taking, say, positive t, and the other ordering is positive u. So you pick the residue at t equals 0, and only this guy contribute. And if you go the other way around, which is here, because of this factor, this term does not contribute. Because there is no residue, there is no pole. So when you take discontinuity, graviton does not come. And so if you compute the commutator, you get exactly this combination. So if you compute delta Q, you have exactly this difference of these two guys. Hello. Which is E3 Q1, E4, Q2, minus E3, Q2, E4, Q1. Then you get a 1 from graviton. And this is the statement that Gauss-Bonnet theory has non-commutative shocks. And then you have a contribution of all stringy modes. And this is equal to 0. So the residue is equal S minus 2, S plus 4n, whatever, S, n plus 1, S plus 2n minus 2, and you have here S over 2 Pohammer symbol square, n factorial square. This sum converges for, so this guy behave at large n as n s minus 3. So for s larger than 2, whatever, s less than 2, this sum will converge. And you can indeed check that this relation is satisfied.
This calculation for theory of gravity with the Gauss-Bonnet
Yeah. Yeah.
I should get a factor of t minus 4 somewhere.
Yes, you will get it here. Because I'm proportional. Yeah, of course. Yeah. The problem is that so this non-commutative 3-point coupling, it will just turn identically 0 in 4 dimensions, and you will not get anything. Yeah. Now and in CFT, this is a statement that A-neck operators commute. This is the analog of this statement written. This is this statement inserted in the OPE. Now I think I will try to wrap up. So I guess.
Let me just
Yeah.
Interestingly, you could have asked East about what happens at large T.
Yeah.
Doing some gross bending kind of analysis.
Yeah.
This is tree level maybe.
Well, this is Gross-Mendez fixed angle. This is Reggie.
Yeah, but you could you really just want a saddle point.
He's talking
Not higher T.
Yeah.
So, and you will get a saddle point if you take T large enough. As long as
Sorry, I thought this is known. Forgive me if it's not true. I thought it's only known and was done for fixed angle, which is S and T are both large.
you simply get a saddle point. You see,
Yes.
you don't get a saddle point for large.
No, I'm not sure. Reggie is.
Because you're saying maybe
Yeah, because there is the quantum corrections to alpha of S, the Reggie trajectories.
Yeah.
So I don't think that's.
I see, because you don't get a saddle point contribution at all. It's not.
Yeah.
I mean, the exponent doesn't become large. Presumably that's not much. All we're using is the fact that when you write down to sheet integral, you get an exponent which is which becomes large because T becomes large. But presumably what you're saying is that the angle also becomes small at the same time. You don't get.
Yeah. At least I think, well, surely at genus 1, people computed correction to Reggie trajectories in string theory, and you get some imaginary part because resonances get unstable, but it's still sub-exponential, and I think you can still write it.
What was this label little n in this?
Yeah, so this comes from, you see, this has the string modes. So this is labeling the residue at t equal to n.
Yours is entirely at tree level.
This is tree level, so in general,
Postulating that this will also hold.
yeah, we imagine that this is, for example, we can take, instead of tree level string theory, we can take electrodynamics with electrons. If we integrate out the electrons, we should get correction to the 3-point coupling. So in this case, the same problem, which is the minimal coupling, will be fixed by the contribution to the discontinuity of the pairs of electrons and positrons. That's
I asked this question, but this P-level string theory is not
yeah. Right. Yeah. Yeah.
That's sense.
Yeah. So I would expect, well, again, this is a rigorous in CFT. Here, I would imagine that this dispersion relation holds. And then if you take a weakly coupled string theory, even in G string being small, this is the right picture for the discontinuity.
I missed the conclusion. So here, I guess in the heterotic case, delta Q is not 0.
No, delta Q is always 0 in string theory. The difference is that in heterotic string you have 1 here, which is that you have a non-minimal coupling for the graviton, and then the string most should come and fix. Yeah.
Very non-trivial cancel.
It's in a it's a well, but it all follows sort of from Regge. It's it's a
The high
yeah, and
yeah. But I mean, this is an explicit way to
it's explicit way to see that. Yes.
So from this point of view, it appears miraculous.
Yeah. From this point of view, it's just some miraculous constellations, and also in CFT, this is A minus C. So it's A minus C is equal to these things.
One thing I didn't understand earlier, when you wrote down this convergence relation and the A was smaller than 120 was necessary, or was it also sufficient at large D? When you wrote down discontinuity of A,
Well,
implies one of is smaller than 120 for large D, but is that also sufficient?
I think what we need is, I would imagine that if we don't have extra singularities, if the decay is sub-exponential and this discontinuity is polynomially bounded, this is sufficient. Now I want.
This last one also is related to the fact that the coefficient in front of the Gauss-Bonnet term in heterotic string theory has a plus sign.
Oh no, I just put very, very broadly defined wiggly sign here. So Gauss-Bonnet coupling it can be any sign. It can be signs, but zero has an invariant.
It predicts that it should be plus. I mean, it should be positive.
Yeah, here I don't have cannot say.
It's the coefficient between the graviton 3-point coupling and the
higher spin. Yeah. Yes. Say if you this thing, if you evaluate it, I think at maybe s equal 2, this sum rule, or maybe s equal 1, you see that all the modes with n larger than 1 are 0. So you really get this condition right at 0. So at s equals 0, you get this condition, and but then this first level has a spin 4 particle, and it's important. So you really need high spin particles also, which is consistent with the previous story too. If you look at the structure of 3-point couplings, you can ask what is the minimal set of states you can add to satisfy, and you always need high spin particles. But okay, well, this is this sum rules. We do not have a good understanding of all the implications, and can I take 3 more minutes with just last comment? So there was this observation, or there was a statement.
Sorry. Suppose you were working in just the type 2 theory.
Yeah.
Then the graviton part is 0 and the string theory part is independently 0.
Yeah. So it's trivial. So the commutator is 0 automatically. Yeah.
And both terms separately 0.
Yeah. So I think. So you're saying that. Yes, I only know that the graviton. I only know that the graviton contribution is 0. I don't know what is the structure of this higher spin poles in type 2B. I thought somehow that they're all just zero. If you compute the commutator, so that at each string level, each commutator is zero. That's what I thought.
Okay, thanks.
So what? Yeah.
You know what consider is Lovelock theory?
Well, Lovelock theories, they violate that.
They violate.
Yeah. Well, everything violates this that is non-minimally coupled. You really have to add this higher spin tails. But whenever you make a coupling non-minimal, you have to start adding things.
You have to make sure the higher.
Yeah. You start the thing. I think maybe that was not familiar was that, or because people never computed these things, is that if you start making coupling non-minimal, you start messing up with the Regge limit. In a sense, it's a Regge limit of a 6-point amplitude, I guess, which controls the propagation through this couple of shocks. So one last comment I wanted to make is that, well, people discuss in CFTs this kind of relation, A minus C over C is a 4 to 1 over delta gap squared. So how does this come about from this reasoning? And the idea is that you can ask, is there interpretation of the superconvergent sum rules in terms of this partial waves? Well, maybe you know, yesterday we were discussing that in the Froissart-Gribov formula you have integrals over discontinuity. So it's natural to expect that maybe there is a relation between partial waves. This is an also integral over discontinuity. And for the scalar case, for the scalar amplitude, you can check that I briefly mentioned in the Froissart-Gribov there are this continuation from even spins and continuation from the odd spins. You can check that this superconvergence condition is a statement that F minus, which is at odd spin, at j equal -1 is equal to 0. That's related to the statement. And in the CFTs, it's related to the statement that if you have whatever C partial waves for CFTs, if you set C minus, and for gravitons, it will be j equal 3 is equal to 0. This is not obvious, but believe me, if you reshuffle all this, you get that, you know, if you have a OP of stress tensors, you have this, everything is analytic and spin. And if you take the odd signature Regge trajectory and send it to 3, whatever, you get the superconvergence just statement that at this particular spin that it should be 0. And then the idea is the following. So if you, let me take this condition, and remember in the Froissart-Gribov integral, you have something like this. The integral, say, from the, let me consider contribution of heavy states into Froissart-Gribov integral. So there is here, say, delta gap or m gap squared. And then there is this factor which, well, it was t yesterday, t minus j. And have some discontinuity. And so if we have a non-commutativity of gravitons, say something like lambda Gauss-Bonnet, by superconvergence, its non-commutativity should be cancelled by non-commutativity of the other guys, and J should be set by 3 for gravitons. Sorry for being a little bit vague here, but and now you can, and here there is something like discontinuity in the T channel minus discontinuity in the U channel. So U channel takes care of the integral is from the gap to infinity, and there is also part from minus infinity to minus gap, and this is this minus. Now this, in the relevant region, so these guys, let's say they are positive, so then you can bound this from above, this thing by, first we pull out 1 over t out of the integral, because t starts from gap to infinity, so we can bound it by 1 over gap. And here we get the same integral, t minus 2. And this we can bound by putting a plus here. Okay. And this 1 over gap, and again, this in the Froissart-Gribov formula, this is nothing but now partial wave with from the even spins, because it's equal to now, j equal 2. And so this is related to the partial wave which knows about the graviton pole in particular. So this is a partial wave which controls graviton. And modulo some subtleties that you expect that to reproduce a graviton pole, this guy behaves like 1 over CT. And therefore you get a type of bound that lambda Gauss-Bonnet should be less than 1 over gap square over CT. It's the same type of wiggly bound that we got before, but here it comes about from the fact that the superconvergence is a statement about odd signature radial trajectory at spin 3, and in the Froissart-Gribov formula, spin buys you a factor of 1 over gap. So, but this was probably.
But this is stronger because you also get a 1 over n.
Yeah. So this part also. So this 1 over n. No, it's actually this how people, I think. So if you pull C here, yeah, in the usual the way people. So in this, if you consider Gauss-Bonnet correction to the GR, the way we consider is that we have an overall small g Newton, and then we add a Gauss-Bonnet term. So if you wish, this 1 over CT is just a statement that we have a correction on top of it. So it's the same thing. Sorry.
This is the mass of the lightest
string.
particle.
Yeah. So if we assume is that we have a gravity with a gap. So this is the state. And there is a wiggly line because I mean, this is a toy computation. For the fall for gravity computation, it's much more complicated. And say we haven't done it with all spin. It's still to be done. But I'm trying to illustrate where this factor comes from. But in principle, so okay, this is what you get. This is a gap. This is a mass of the lighted state. And sorry,
what is CT is what?
Sorry, CT is it's G Newton. It's the same as, so the idea is that we take this condition and we write the non-commutativity of gravitons as non-commutativity of everything else, and then we relate it to partial wave of spin 2. And there is this picture from Froissart-Gribov that the partial wave of spin 2 should contain a graviton pole, and the graviton pole has a residue which is 1 over CT.
Understand. So this is alpha Gauss quantity normalized in this should be a dimensionless number. I should think of this as m Planck by m gap squared, this alpha Gauss quantity.
Yeah, well, I don't know if I can. I mean, in CFT, I would just write here 1 over lambda delta gap in ADS radius. So in flat space, in flat space, I'm not.
But if that's
sure.
Newton, you should think of it as m Planck by m gap squared. So
Yeah.
That's huge. I mean, that's huge, right? That's like 10 to the.
It's small.
That's huge. M Planck.
No, it's 1 over Newton square. 1 over n square.
I'm trying to see where the dimensions.
Delta
Yeah.
gap is
Yeah.
order 1, and then there's a 1 over n square.
Yeah.
So what's the kind of delta gap?
So.
Gap is order 1, and C.
Well, I guess delta gap is of order of whatever string, yeah, lambda to whatever 1/4, and CT is 1/n squared.
I just trying to understand how in that space, how the electron, for example, would be. So if I take the electron and try to understand where.
Okay, we will probably continue a long way because yeah, for electron I'm not sure. Yeah.
The normalization of the Gauss term is how you have R squared and you normalize by 1 by n Planck with the appropriate power of n Planck, or and alpha GB is the dimension.
Okay, so here, if you let me, if I yeah, I guess I was mostly thinking about CFT, so everything was dimensionless. So it's just a gap of just dimensionless. So naively, I would just put here radius of ADS, but don't trust me on that. So I think that I think the punchline is that we're getting the same condition as we were getting before. So the normalization should be that we write 1/g Newton in front of the action. We write, if we write 1/g Newton in front of the action, and then we write R plus alpha Gauss-Bonnet, then there is no 1/CT, then this is the usual one, Gauss-Bonnet. So if you wish, this is I think, something like we write R plus lambda Gauss-Bonnet. So what because
So maybe that's.
So if I write like this, then there's no this guy.
I see. Okay. So let's put the cosmological scale. So in those units, this is a huge mass because the mass of the electron is huge compared to cosmology.
Yeah. So the Gauss-Bonnet will be tiny. Yeah.
But gravity is very weak, so that's why I'm still trying to mean it's we know gravity is very weak. Is this a strong constraint or a weak constraint on phenomenology? That's what I'm trying to say.
Yeah. I would think that it should be a weak constraint, because if you write any effective theory, well, surely if you write some effective field theory. Well, there is R cube. We can consider R cube. Yeah. So we can consider some diagram like this. So that's how we generate this coupling in the standard model, right? So we take some state, we integrate this loop and this 3-point coupling. So if all these couplings are just say usual G Newton, so this is already very tiny. And then there will be an extra scale of 1/mass of a particle, so you'll get something that you expect from a field theory, I guess.
I'll be there in 5 minutes.
But I guess in principle it says that if there is some extra sort of bare term, which you would like to add, say. Actually, one question I'm not sure about is that note that here we are not computing the amplitude, but we're computing the discontinuity in the T and U channel. And I was wondering if this improves the situation with infrared divergences. I don't know, but usually taking discontinuity helps, and maybe, but I'm not sure. But here, so if we want to, so surely we have in any effective field theory this type of diagrams. But then, of course, you can add something there where you said, okay, this is a new constant of nature, this non-minimal coupling, and then this should be tied to some extra states.
I'm a little confused. Because we're in that space again and K is not conformal, there should be some scale.
Yeah. Yes. So this is dimensionful, right? This is lambda Gauss-Bonnet is 1/mass gap, exactly as it should be.
There should be some renormalization scale for this coupling.
Well, sorry, 3-point amplitude does not have functional dependence and does not have RG scale. It's just a constant of nature. Because it's on shell, there is nothing that you can divide upon. Thank you.
So, yeah, just going back to the relation between the causality and this.
Yeah.
Did you get? I mean, I'm just wondering whether, when you look at it from the point of view of these vertices, I mean, Subrat was also asking about this commutator.
Yeah.
Asymptotic thing. So, yeah.
A priori, it's a little bit different. So let me remind what. So how does it work? So in the causality story, we consider a 4-point amplitude. So there is this 1 over q squared. You go to impact parameter space, you pick the pole, so q squared becomes effectively null. And we have, again, the product of the amplitudes, something like 1, 2, x, a, 3, 4, x. So where x is what exchanged here. And this defines, in principle, an operator. Let me call it a Shapiro time delay operator, whatever, phase shift operator, ij, which acts in the space of polarization tensors. And then we wanted to say that, I guess, it's a positive definite operator before, so that Shapiro delay is always positive. So here, if you wish, it's a cut. This is a probe. This is a shock. So we are cutting it here. This is a causality paper. We were cutting this channel. In particular, I think the momentum which exchanged between these two guys was very small. So the invariant mass was, say, t equals 0, if you wish. So here, what we are doing is a different thing. So here we have the shock, and we are cutting this channel. So now we have two shocks, and we are cutting this channel. And the invariant momentum between these two guys is actually large. So, well, it's not large, but we are summing over all states here. So it's a priori it's a slightly different. It's a different story, and it does look different. For example, here this operator depended on impact parameter. And here, well, here we have dependence on this S. And also here, note that from the point of view of what I was telling you today, we were studying here kind of shocks, different type of shock states. So we just consider this type of amplitudes in the causality paper. So we were saying that this object where a shock is different, so we have high spin states in this channel. Whereas here, we have high spin states in the other channel. If you wish, it's so in here, when you have a, yeah, well, I don't know how to say. Let's.
Yeah, I mean, yeah, they're little different. different in
yeah.
Somehow it seems similar.
I think that maybe in CFT, so our previous thing is related to positivity of ANAC operators, and this is related to commutativity of ANAC operators, which in principle is a different thing. For example, yeah, it's an extra. I guess we want to say that there is an extra consistency conditions, which is that in a CFT, in a UV complete CFT, or if we believe flat space story, ANAC operators commute. And in say Hoffman-Maldacena paper, they say that this is obvious because these guys are space-like separated, right? Because if you draw what is ANAC operator, it's inserted at some y minus equal to 0, so y plus equal to 0, y minus, and some y. So if you put two operators at different transverse positions, y1 and y2, they're space-like separated. But that's too fast, because from the point of view of light ray operators, when you do this, you're putting two light ray operators on top of each other. So if you draw it on a cylinder, you have one operator, and then you have another operator, and then you want to limit or shrink this to 0, so you put them on top of each other. You have to worry that this limit exists, that it's commutative, and in general, it's not commutative limit. So light ray operators do not have to commute. But you can show that for ANACs, they do.
Yeah, I was wondering, not in terms of the Shapiro time delay, but maybe what Subrat was saying,
yeah.
You can incorporate this as some commutator and limit just as a usual causal commutator. If that's
well, I guess in ADS-CFT, this is very precise. So here, this is our scry. So we want something like this, which looks a bit different.
These are spatial, but even though there's this subtlety, but
yeah, so first start, there is a region where time-like, or when you put them on top of each other, there is this region that they touch at infinity. So you might be worrying that it's too fast, that yes, indeed, for finite y, they're space-like, but at infinity they touch, and then if you resolve it and go back, then you see that this introduces non-commutativity potential.
Yeah, but it's not obvious that non-commutativity is due to causal,
Yeah, it's not obvious. No. It's a priori, it's a different non-commutativity, and the way it works is different also. Say, here we had some vague sum rule depending on the impact parameter. Here there is no impact parameter, it's an identity. And it sounds like a different condition. Sounds like that this is an extra condition that one has to impose. But say in CFT, for example, this condition, as I try to emphasize, this is a maybe simpler expression of a correct Regge limit of the theory. So, and I guess coming back to our previous, to the causality analysis, you could have asked, can you arrange with non-minimal couplings for such a medium where the amplitude or delay will be advanced? And the statement is yes. If this is violated, then you will be able to arrange such a way that you will have Shapiro time advance. I think this is a statement one would like to, I would like, it looks like this because this is tied to a Regge limit, and this Shapiro analysis is just a statement about Regge limit. We have this delay being linear in S, and then when in the signal model it leads to this delay if you consider how it acts on the wave packets. But if you put any higher power here, you get here this power alpha, and if you have such a medium with alpha larger than 1, you violate causality. And this is the same as the bound on chaos. Same exponents that you have to get here. And I think that if we get the Regge, so there is a non-trivial part of exponentiation, can you exponentiate or not? But then in CFT, we know that we can just forget about exponentiation, just talk about Regge limit. And then you see that you get just again the same conditions that with this commutator being non-zero, you get here alpha larger than 1. So I would say that they're related indirectly, but you have to make it a problem with causality, you have to consider more complicated medium generated by this pair of shocks from the kind of 6-point amplitudes. So you cannot. It's not just enough to consider the 4-point amplitude. It's some sort of consistency conditions of 6-point amplitudes, or 6-point correlators, or whatever.
Hi, Sasha. This is from TIFI, Mumbai. So one comment and one question, please.
Yeah.
The comment is that 5 of us here, Abhijit, Gade, Indranil, Lavneet, Shubham, and myself have been working on a project that is that has some relationship to what you're talking about.
It's good. It's good. It means that there are 3 of us, because there is also a group in Amsterdam. I know. So.
Okay, I'm not sure how big the relationship is, but what we're doing is to use a principle similar to the one that you're imposing about how fast the amplitude can grow.
Yeah.
The principle that in the ADS context follows from the chaos bound.
Yeah.
To constrain 4 graviton couplings that are contact 4 graviton couplings. So not like the Gauss-Bonnet sort, but the R to the 4 sort. Turns out there are 10 such terms in asymptotically high dimension. There are 10 such coupling kind of terms, and we think we have an argument saying that all of them are ruled out by if you have a finite truncation in derivatives. All of them are ruled out by this asymptotic growth condition, which in an ADS context is implied by the chaos bound. Okay, so but I had a question related to this. These contact type of terms would seem to give you contributions. Let's say just classically, these contact type of terms would seem to give you contribute to your 4-point amplitude that have no discontinuity, because they're completely analytic.
They do. So they do not contribute to the sum rule. Yeah.
Your sum rule does not seem to say anything about these terms.
Absolutely right. We do not say anything about those terms.
So when you say that this rule, this commuting of shock waves, is a restatement of the growth, that's true somehow for the non-analytic pieces, but not for the purely analytic pieces.
Yeah. Sorry. So in this particular kinematics, it's a restatement, but the non-growth is probably stronger, as you say. Yeah. So here we took some kinematics and we saw that non-analytic, the non-growth of non-analytic part leads to that, but there might be an extra conditions on the.
But at one loop, this 4-point guy will.
We're able to constrain the 4-point.
Yeah. Is it true that at one loop, the 4-point guy will contribute to distinguishing from one loop?
We can't hear a thing you're saying, Subrat.
I'm just saying, you might try and draw a loop graph like the one that Sasha is drawing now. And that would contribute to the discontinuity. So at tree level, you're right, it wouldn't, but at higher orders in perturbation theory, it might.
Yeah, it might at higher orders in perturbation theory. So we were taking the point of view that could you constrain, from our point of view, the question that we were asking was, can you constrain classical theories of gravity? What can you say about classical theories of gravity? Or in some effective action kind of point of view? In the quantum effective action, what can you say? And at least from that point of view, these terms are not constrained. So just classical gravity with a 4R term would not be ruled out, but R to the 4 term would not, the R to the 4 term would not contribute to this discontinuity. Yeah. Whereas we believe it is ruled out.
Yeah. I think this has some extra, so there is this contribution, but.
Yeah, I agree. But the term is what the classical term forces you to add by unitarity. I mean the diagram that Sasha has drawn. So this just the one loop diagram. So I mean I agree with you. I'm not disagreeing. But the higher order perturbation theory things may not be so hard to take into account. Maybe in his approach.
Yeah, but perhaps. But we could also ask the question: what? Suppose you find the exact quantum effective action for gravity, and you ask which terms in this quantum effective action are you constraining? Seems like you're not constraining the analytic pieces.
Yeah.
Whereas the growth constraint constrains everything.
Right.
questions from Bombay or from anyone here?
Okay, so everyone wants to get lunch, so we'll stop here. Thank you very much, Sasha, for a great set of lectures. Thank you.